Have you ever just looked at a solar panel and really wondered what's going on inside that dark, silent piece of glass? I mean, it seems so simple, right? But its story? Oh, it's this incredible journey through accidental discoveries, deep quantum physics, and some seriously clever engineering. So let's dive in and see how we finally taught light to work for us. For almost all of human history, the sun was just, well, it was heat and it was light. That was it. But this really powerful question started to bubble up in the minds of scientists. Could you take sunlight itself, with no fire, no steam, no moving parts, and just turn it straight into electricity? Answering that question was going to change everything.
And the funny thing is, our journey here doesn't kick off in some fancy high-tech lab with a grand mission. Nope, it starts way back in 1839 with a total surprise, an accident really, that planted the seed for our entire energy future.
So meet Edmund Becquerel. He's just 19 years old and he's tinkering with some metal electrodes in a chemical solution. And as he's working, sunlight hits his little setup and he sees something that, by the science of his day, was basically impossible. An electric current just appeared. Out of nowhere. He had no clue why.
What he had just stumbled upon is what we now call the photovoltaic effect. Let's just break that down real quick. Photo, that comes from the Greek word for light, and voltaic for electricity, named after Alessandro Volta. So light creating electricity. The problem was, the how of it all, that remained a complete mystery for decades. So Becquerel had found this puzzle that the science of his time just couldn't solve. The key to unlocking it wouldn't be found for years and years, until one of the greatest minds in history came along and completely changed how we think about light itself. And man, the road from that first little spark of discovery was a long one. Think about it. After Becquerel's accident in 1839, it took more than 60 years for Einstein to even come up with the theory in 1905. And then, it took another 50 years for Bell Labs to finally build the first practical solar cell. So what was Einstein's huge idea? Well, he said that light isn't just a continuous wave. It actually arrives in these little individual packets of energy called photons. You can almost think of them like tiny bullets of pure energy. And if one of those photon bullets hits an atom with enough oomph, it can literally knock an electron loose. This one idea, which, by the way, is what won him his Nobel Prize, perfectly explained Becquerel's mystery. Okay, so with the theory in place, the challenge became a practical one. What's the best material to catch these photons and then harness those electrons they knock loose? The answer, it turns out, wasn't a metal. It was a specially engineered semiconductor, silicon. The very first solar cells were terrible, less than 1% efficient. So when the folks at Bell Labs figured out how to use engineered silicon back in 1954, they hit an absolutely mind-blowing 6% efficiency. That giant leap was the moment everyone realized, wow, okay, solar power could be a real thing. So how did they engineer it? They used this process called doping. Basically, they took super pure silicon and they intentionally added tiny, tiny amounts of impurities. On one layer, they'd add phosphorus, which brings along extra electrons that are free to move around. That creates N-type, for negative silicon. Then on the other layer, they'd add boron, which actually creates little holes, spots where an electron should be, and that's P-type for positive silicon. And right here, this is where the magic happens. Where these two different types of silicon touch, the extra electrons from the N side immediately rush over to fill the holes on the P side. This little migration creates a permanent, powerful, one-way street for electrons right down the middle. It's an internal electric field. This gate is the engine of the entire solar system. So it all comes down to this really elegant three-step dance. First, a photon from the sun smacks into the silicon. It knocks an electron loose, and that leaves behind one of those holes. Second, that electric field we just talked about acts like a bouncer at a club. It instantly shoves the free electron over to the N side, and the hole over to the P side. And crucially, they can't cross back over. And finally, when we connect a wire between the two sides, we give all those separated electrons a path to travel. And that flow of electrons, that is an electric current.
Now, a single one of these little cells doesn't produce a whole lot of power on its own. Not enough to power your coffee maker anyway. So to make it useful, we have to scale things up, combining hundreds of these tiny engines into the big panels we see everywhere.
It's actually a lot like using batteries. You wire the cells together in a chain, in series, positive to negative, and that builds up the voltage, which is like electrical pressure. Then you take those strings of cells and wire them together in parallel. That increases the current, which you can think of as the volume of electricity flowing. Put them together, and you get a powerful, useful stream of electricity. Of course, these super thin silicon cells are incredibly delicate. They wouldn't last 5 minutes out in the wind and rain, so they get sealed up in this protective sandwich. You've got tough tempered glass on top, a kind of shock-absorbing polymer in the middle, and a rigid aluminum frame all around to make sure they can survive on a roof for decades. And you better believe the story didn't stop in 1954. Not even close. The evolution of solar panels is this ongoing story of constantly pushing the limits of physics and material science, trying to squeeze more and more energy out of every single sunbeam. I mean, we've seen just incredible progress. The first generation panels, made from these big, pure single crystals of silicon, they're the workhorses today, hitting efficiencies over 20%. Then you've got second-gen thin film, which is cheaper and even flexible. And now, third-gen stuff is coming out, like PERC and bifacial panels that can capture light from both sides. They're pushing efficiencies past 30% in the lab. The goal is always the same: get more power out of less sunlight. There's just one more critical piece to the puzzle. Your solar panel produces DC or direct current, but your home, your TV, your fridge, they all run on AC, alternating current. The inverter is the electronic brain of the whole system that does that conversion, making the sun's power usable for your home or ready to be sent back to the grid.
So after all that incredible science, where are we at today? Well, a typical modern solar panel you'd buy right now has about a 20% efficiency. That means for every 100 photons of sunlight that hit it, about 20 get turned into useful electricity. The rest, well, it gets reflected or just turns into heat. And yet,
even at only 20% efficiency, the sheer scale of the sun's energy is just staggering. Get this, in one single hour, more solar energy hits the surface of the Earth than all of humanity uses in an entire year. The fuel is, for all intents and purposes, limitless. So the next time you look at a solar panel, you're not just seeing a piece of hardware. You're really seeing quantum mechanics made practical. You're seeing engineering at the atomic level, scaled up to power entire cities. What you're really seeing is humanity finally figuring out how to just quietly and elegantly borrow a little bit of energy from our own star. And that, really, is the whole story right there. The power was always there, flooding our planet every single day. We just had to follow this incredible path from a teenager's weird little observation through Einstein's brilliant mind to finally understand the language of light. The sun was always ready for us. We just needed the science to learn how to listen.